Hi everyone, welcome back to another Planetarium live stream. My name is Jessica, I am the director of the Planetarium, and with me are two familiar faces that I will let introduce themselves, and we will start with this guy to my left.
Hi, I'm Eli. I'm a physics undergraduate student at UMD.
Hi, I'm Lindsay. I'm a physics graduate student at UMD.
So tonight we're going to be talking about one of my personal favorite topics. It's exoplanets or extrasolar planets, planets around other stars. We're going to be taking a look at exactly how we can find them, and then we'll also look at some of the interesting and weird ones that we have found, because there's quite a few. There are some really cool ones. As I'm getting set up, if you do have any questions throughout, leave them down in the comments. Eli, you're going to be checking those?
Yep.
Yep. Okay, just forgot to double check before we started. Eli will be watching for those and will let us know if you do have any questions, or we'll take some time at the end to answer as well. So let me get things set up. And we will get started. So as I said, we are going to be talking about exoplanets, planets around other stars. And these are not easy to find. Just think about how small our planet is compared to our sun. It takes, now I'm blanking, 109 Earths to fit across our sun. They're tiny compared to stars. And plus, stars also shine very, very brightly, and they can drown out any reflected light that may be bouncing off of the planet. So these things are not easy to find, especially if you're trying to look for the planet itself. And so instead of trying to find the planet itself, one of the ways that we search for them is to actually look for the effects that a planet has on the star it's orbiting around. And we're able to use that kind of circumstantial evidence to infer that there is a planet there. And so one of these methods has to do with gravity and gravitational tugs. And it starts off with understanding a common phrase we use. I used it just a few minutes ago, that a planet orbits a star. That is not entirely correct. So what actually happens is two things orbit a point called the center of mass. It's like the balance point. If you were to put them on like a seesaw, that center of mass is where the two would be balanced on that seesaw. And so if we have two objects that are the same mass, like we have here on the left, that center of mass is smack dab in between them, right in the middle, and the two orbit around that point. Now, if one object starts to be a little bit bigger, a little bit more massive, then that balance point shifts closer to the more massive one, and the orbit may look something like this, where again, both are still going around that center of mass. Well, if we keep going more extreme, we end up with a really big object, like a star, and a really small object, like a planet. Because the star is so much more massive than the planet, that center of mass can actually sit inside of the star. And so from our viewpoint, the planet is in fact orbiting around the star, just like we say. But what's not said there is the star is also kind of wobbling, because it's also going around that center of mass. And so this is one of the things that we can look for when we're searching for planets, is we look for a star that's wobbling, because that means it's orbiting a center of mass, which means there has to be something else going around it. And this method is pretty useful because it can give us more information than just there is a planet there, because gravity has to do with mass. It has to do with distances. That all determines how strong gravity is, and that's going to determine how big of a wobble there is. We can find out things like how massive the planet is. We can figure out how far away it is. And all of that is important if we're especially trying to find a planet like ours, like Earth, that could have life on it. Now, there are still some struggles with this method because the wobble of the star is very, very small. It's not like we can just stare and see a star and physically see it wobbling back and forth. There are a few that we could do that with, the closest stars, but most are too far away. So we have to use something else to help to indicate to us that that star is wobbling. And that's where the light coming from the star plays a role. If you have watched our show a few weeks ago, Learning from Light, one of the things we talk about is how one of the things that we can learn from the light coming from an object is if it's moving and how fast it's moving. Because when a star moves towards us, or towards you, its light gets shifted to shorter wavelengths, to bluer colors. And if the star is moving away from you, its light gets shifted to longer wavelengths, to redder colors. And so if you have a star that's wobbling, it's going to be moving towards and away, and towards and away. And so you're actually going to see its light shift blue and red, and blue and red, back and forth. And so by seeing that shift back and forth in the light, that's how we can detect that wobble of the star, to tell us that there is a planet there, and also tell us, how massive the planet is, how far away it is, all of that sort of stuff. So that's one method, one way that we can find a planet orbiting a star. The other method is what we call the transit method. And the idea behind this is, in some cases, there is going to be a planet and star system that is oriented just right so that the planet passes in between us and the star it's orbiting around. And as it passes in front of the star, it's going to block some of the star's light and cause the star to temporarily dim before it moves past and the star goes back to its regular brightness. And so one of the things that we search for when searching for planets are stars that periodically dim over time. And they continue to do so in a regular pattern. So like every 2 days, we see it drop in brightness for a little bit, and then it comes back up. And then 2 days later, drops again, and then comes back to normal. And that's important to see it repeat, because stars themselves don't always stay exactly the same brightness. There are things that can cause it to vary. And so just one random dimming event doesn't necessarily mean planet, but a event that happens regularly every 2 days, much more likely to be caused by something like a planet. Now, as you can see here, one of the things that we can learn from a transit is actually the size of the planet, its radius. Because a bigger planet is going to block more light, causing the star's brightness to dim even more. And so we're able to find out how big the planet is from this sort of event. Now, these are rare. I'm blanking on the exact phrase that I want to use. But we're missing a lot of planets by searching just for transit events, because these only work for systems that are lined correctly, lined up, so that you do have the planet pass in between us and the star. If we have a system like this, and you can see me in the camera there, where it goes around like this, it never passes in between us and the star, and so we won't detect it. And so it's only for a small subset of systems that are oriented just right. So there's a lot we're missing, but it's another way of detecting them and finding systems. There's pros and cons to all of these. So those are our two main methods, the wobble of the star, and then looking for that drop in brightness from that transit event. And so we have kind of two space telescopes that are dedicated to searching for planets around other stars. The one that you might be familiar with, that's kind of the more known of the two, is the Kepler Space Telescope, which launched back in 2009 and was retired a couple years ago in 2018. Now, its mission when it first launched was to monitor the brightness of 150,000 stars every 30 minutes. Yeah, every 30 minutes, it took measurements of the brightness of 150,000 stars and then sent us that information. That is a lot of information to comb through. And we are still going through it because it worked for, over 9 years. There's a lot to still see. And so far, it has found over almost 3,000 planets have been found with the Kepler Space Telescope. And then we have another 3,000 that are candidates, meaning we've seen some evidence, but we're still looking through the data to confirm that kind of regularity and make sure it's not some random fluctuation. And so, there's been a lot of planets found with Kepler. Now, the newer mission that is still active is Tess, the Transiting Exoplanet Survey Satellite. Now, Tess launched back in April of 2018, and it has an even bigger job than Kepler had. Kepler, as we said, monitored about 150,000 stars. Tess is watching almost 85% of our entire sky, looking at over 400 times more stars, not more stars, but more kind of area than Kepler was watching. So it's a lot of information coming from Tess. And since this is still a relatively new mission, we haven't had as much time to comb through the data. It also hasn't been watching as long. And so we don't have a huge number found yet. Last I checked, it was still under 100. But that's just the earliest. We have several thousand candidates that we're still combing through the data. And as Tess continues to work, we will see more and more and more coming out of it. Because you have to think about it. The first kind of planets you're going to find are those that are orbiting very quickly, right? Those that make orbits, say, every couple days or every couple weeks, because those are easy to confirm, yes, that's a regular event, because you only have to wait, a month or so to see that happen several times. Whereas if you want a planet like Earth that takes a whole year to orbit, you have to wait several years to see that event happen a few times before you can confirm it. So we see a lot of the close planets, a lot of really fast, close by planets are found right away because they're easy. But as we continue to watch over the next few years, we're going to find more and more and more with Tess as well. Which is also why it's important to kind of keep watching over a several year span so that you can find these things. Those are our two. Kepler, which is not active anymore, but we still have a lot of the data we're working through, and then Tess, which is active and continuing the hunt that Kepler started. And so with that, let's start talking about some of the interesting planets that we have found, because with, thousands and thousands of planets confirmed, there are bound to be some interesting ones there. I will pause for a second and check if there have been any questions that have come in before moving on.
Nope, nothing yet.
All right. Well, the first planet that we're going to start with is not so much weird as it is hopeful, I guess we'll say, because of course one of the things that we want to find when searching for planets around stars is we want to find another Earth. We want to find a planet like ours, not only just to show, whether it's likely for life to be out there, but, we may be in need of a second home here soon. So it would be nice to know if there are places that we could go to. And so the first exoplanet that I'm going to tell you about is Kepler 186f. You will notice these exoplanets don't have super interesting names. They tend to be named after the either mission or the star that they're around. So in this case, this planet is around the star Kepler 186. And the F designates that it is I have to remember the fifth planet found around this star. So what's exciting about Kepler 186f is it was one of the first Earth-sized planets that we found that happens to be in what we call the habitable zone. It's the distance from its star that would give it Earth-like temperatures, meaning with an Earth-sized planet and Earth-like temperatures, we could have something Earth-like with vegetation and lots of liquid water on the surface and all stuff like that. Now, we don't know what the surface actually looks like, but it does make it a good candidate for a possible, second Earth out there. So there are 4 other planets in this system, and you will notice compared to our solar system, this one is much more compact. The planets sit a lot closer to their star than our planets are. You can see that here Kepler 186f is more like the distance of Mercury, much closer. But it's still Earth temperature because the star in this system is not the same as our sun. It's a cooler star. So you do have to be closer to still be as warm as the Earth is. And so it's this little compact system, and here's an artist's rendering of what it may look like. It's a little bit bigger than the Earth, but pretty close, and so that's exciting. Now, after that, because as exciting as this system is about 600 light years away. So it would be an incredible voyage for us to try and get there. That makes it maybe not our best, second home. We want to find something that's a little bit closer. And so when we found this next planet, we got very excited because it turns out that the star closest to us, Proxima Centauri, has a planet around it. And not only does it have a planet around it, it has an Earth-sized planet that also sits within the habitable zone, that is at the right distance from its star to possibly have Earth-like temperatures. And so this is the closest exoplanet that we have found to us because it's around the closest star and it's possibly Earth-like. This one is a little over 4 light years away. And so while it would still be a voyage, it's definitely the easiest of any of them to try and get to. If we could just figure out how to get spacecraft to go at least, a portion of light speed, then this voyage wouldn't be as bad. We'll see. But it gives us hope. All right, so after our Earth-like, which are exciting, let's head into some other kind of weird ones, some actual weird ones. And so the next one to look at is Kepler 16b. Now, this one is exciting because it was the first planet found around a binary star system. So you have a binary star system is two stars that orbit around each other. And so this was the first planet found orbiting around this A2 star system. And this was extremely exciting because we weren't 100% sure if a planet could have a stable orbit around a multi-star system like this. And it also opens up the possibilities for how many planets could be out there, because the majority of stars are not single stars. Most of them are in binary systems. And so by seeing that, yes, you can have a stable planet orbit around a binary star system, that means that there could be even more planets out there than we first thought. And this also brings to life Eli or Lindsay, you're going to have to remind me the name of the planet in Star Wars.
Oh, which one?
With the Tatooine.
With the double sunset? Okay, I just want to make sure we're doing that and not the next planet you're going to talk about. Yeah, Tatooine.
No, Tatooine. Yes. That planet with the double stars, double sunset. That is a real thing that is out there. So it's not so much fiction as we might have once thought. All right, so moving on to some really crazy ones. We are going to head to Kepler 10b. This was the first confirmed terrestrial planet, meaning rocky, like our Earth is. However, it sits about 1/20th the distance that Mercury is from our sun, and it is orbiting around a sun-like star, which means it is really, really close to a very hot star, which makes it an incredibly hot planet. Daytime temperatures reach almost 3,000 degrees Fahrenheit. So we have a daytime of basically just molten rock. So it's a literal lava world. But the nighttime temperatures drop down to almost -400 degrees Fahrenheit. So we have a very crazy world of really fire and ice here with Kepler 10b. So not somewhere that we'd want to go visit, but it definitely makes an interesting place to kind of look at and study. So we've had our world of fire and ice. Our next exoplanet, Kepler 22b, is a possible water world, a world that's really just a giant ocean. Now, we're not 100% sure that this is a water world, but the size and mass do make it very likely. And what's super cool about this one is not only is it a water world, but it's also within the habitable zone. It's within kind of Earth-like temperatures, which means we could have a water world with life, a world full of just aquatic life, which would be really cool and amazing, and I would love to be able to study this one, but it's also like 600 light years away, so I don't think we're going to get all up close and personal with it, but it's definitely cool to think about what could possibly be there.
We got a question, if you wouldn't mind me interjecting.
Yeah, absolutely.
So we just got the question, is there enough data on exoplanets to indicate planet characteristics that appear to be more common or more apparent to exoplanets? For example, 65% of exoplanets are the size of Jupiter, or 50% of exoplanets have fewer than 5 planets orbiting a sun-sized star. Soul-sized star is how they phrased it.
That is a really good question. So from what we have found so far, I know that we can estimate at least 50% of all stars have a planet, have at least a single planet. I don't remember the statistic on multi-planet systems, although we do find a lot of them, as you're seeing as we're looking at some of these examples. But what we're also finding is smaller planets, like Earth-sized, seem to be more common than larger planets. And that makes sense, right? Because a smaller planet is going to be easier to build than a bigger planet. You're going to, it would take more time and more material to build a bigger planet. But all of this is continuing to evolve and change as we continue to search. So that's kind of where we stand right now. I think, I'm trying to remember what the statistic is. I think it's an estimated 20% of exoplanet systems have an Earth-sized, possibly Earth temperature planet. Or no, 20% of stars, I think is what it was. Which with 100 billion stars in our galaxy, that's a lot of potential Earths out there. So yeah, we're finding they seem to be very common, if that's the, I guess, short answer to your question. But yeah. All right. So a few more to look at real quick. The next one is Celt 9b, which has a very dramatic artist rendering here. This is the hottest exoplanet that we have found. It is about 3 times the mass of Jupiter, so this is a big planet, Jupiter-sized or bigger planet. And it is so close to its star that it completes one orbit in a day and a half. And because it's so close, temperatures on this planet exceed 5,000 degrees Fahrenheit, I believe. I have it in Kelvin, so I don't have it in Fahrenheit. 4,600 Kelvin for anyone who knows that. But it's very, 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 very hot. It's actually hotter than some cool stars. It's hotter than sub-stars are. And because it's so hot, it's actually like puffy. The gases in the planet have kind of puffed up, making this a very puffy planet. But it's also constantly losing those gases as it's being stripped away from the winds from the star and just from the extreme heat that also causes gas loss. And so eventually this is going to be kind of dwindled down to a charred lump of rock that's left behind, whatever rocky material may be at the center. So yeah, this is definitely an interesting one and the hottest exoplanet. Nova is here and saying hi as we finish up. Okay, scoot so I can get to my mouse, please. Thank you, Nova. Our next one is one of, I think, the coolest. It definitely does not have an interesting name of HD 189733b. But this is another Jupiter-sized planet. Here again, we have the artist rendering, and we can see they made it this blue color, which we do think it is. Because from our observations, this star, or this planet, is also very hot. It's pretty close to its star, and it's hot enough to melt the silica that is in it, which is basically creating molten glass that rains down from the clouds. But it gets even more bizarre than that, because this is not going to be a nice, gentle rain of molten glass, if you could call that gentle. But the winds on this planet are so extreme that they blow pretty much sideways at about 5,400 miles per hour. And so you have this just slamming sideways winds blowing molten glass around the planet. And that's what ends up giving it this kind of blue color, we think. So just strange and bizarre, but not a place you would actually want to go visit. And the very last two are what I have nicknamed the Bejeweled Worlds. 55 Cancrie E, here on the left, we think could possibly be covered in diamonds. And then Hat P7b over here on the right could possibly rain rubies and sapphires. So maybe these would be good ones to go visit. I don't know. You can make up your minds. These are still pretty hostile. I don't know if I would want to actually be out in a rain of gems. That I feel like would hurt. Um, but that is the last of our interesting worlds and the last of our exoplanet exploration here. So with that, we will come back and see if there are any more questions that came in.
No more questions.
No questions?
Just another response. I'm sorry, I didn't attempt to pronounce the name earlier. I'm gonna try. I'm gonna just say honor. That's the best attempt I'm gonna make. Sorry if I mispronounced that. Just said thank you for answering the previous question.
Absolutely.
Yeah, that's about it.
Awesome. Well, Lindsay or Eli, do you have anything you want to add?
It's crazy. I think it's so interesting to how these like inferences and like these guesses sounds wrong. It's not a guess. A very, very well informed guess are made as to what these planets are like. I think it'd be really cool to actually get out there and see how close we were. It'd be like a little game, like how close were we on this one?
Yeah.
I would think that'd be really fun, but like we talked about there.
But as our technology improves and telescopes improve, we'll get more and more information, which will help either confirm or disprove these early models we have.
Right.
So a lot of these models are based just off on mass, size, and temperature. We are able to use that to infer what the planet might be made of, whether it's more like Jupiter or more like Earth, whether it would have the conditions to like rain sapphires or rain molten glass. All of that comes from things like inferring its composition and the temperature. And so, yeah, it's possible we're wrong, but it also is just fun to think about what crazy things could be out there.
Mm-hmm. Yeah,
So
it's just really cool.
Yeah. Well, if you do have any other questions for us, now is a great time to ask them. And while we wait and see if any more come in, let me tell you a little bit about what you can expect over the next week. So on Saturday, Lindsay is going to be teaching us all about the amazing women in astronomy that made significant contributions to our understanding of the universe and unfortunately do not get the credit they deserve. So she's going to be taking us, bringing them to light and giving them the props that they very much deserve. Next week on Wednesday, we are going to kind of expand from tonight's talk of exoplanets and explore the possibility of aliens, whether they really could be out there or not, and what it takes, we think, for a world to maybe have life on it. And then look at some of the places that might have it. I don't know. We'll see. And then next Saturday, Lindsay and Eli are going to be telling us all about the scale and wonders of our universe. Just how big is it really and what all is out there. Building from that, coming up on September 26th, we have our first trial at an in-person event since the pandemic hit, our socially distanced Stellar Saturday on September 26th from 1 to 3. We will be set up in the parking lot outside of the planetarium. Everything's spaced out, safe, and we will be putting together some activity kits, little mini activity kits for some fun things to do at home. And we are theming this one around the moon since the 26th is also International Observe the Moon Night. And so after our Stellar Saturday, we will have a telescope stream that evening, looking at our moon if weather permits. And then one last thing to say is we are selling these really cute stellar distancing t-shirts to help raise money for the planetarium since we have not been open for several months, and we want to continue to bring you these live streams, but also to hopefully do things like the Stellar Saturday occasionally throughout. So if you are able to support us and you'd like one of these awesome shirts, you can find the link in the video description. So that, I think, concludes everything I have to say. Um, if we have any more questions come in.
Nope, no
No?
questions.
All right. Well, Nova is going to say goodnight with us. She doesn't actually like to be held. She gets very upset when I try and hold her. But she does like to be in the way. Anyway, so yeah, we will conclude it there. Thank you everyone so much for joining us. We hope you enjoyed the show. We hope you have a wonderful rest of your evening, and we will see you next time. So, bye everyone.